All right. Good morning. Okay, so you've just turned in homework number 9. That means that the next assignment you have is homework number 10. That's available now on MU Online, and you've got a little bit less time than usual to complete that one. Rather than being due at 11 o'clock on Tuesday of next week, it's going to be due at noon on Monday, so that the solution will be available immediately after that closes, and you'll have a little bit of time to review the solution and check it against your work before our exam the following day. So we're going to have the exam 2 a week from today, covering chapters 4, 5, and 6. So remember, chapter 4 is where we talked about Euler's equation, Bernoulli's equation, rotational flow, flow visualization, convective and local acceleration. So chapter 5 was a big one. And excuse me, that was all in chapter 4. Chapter 5 is an important chapter, but it's just limited mainly to a single idea, the idea of continuity. So to make things interesting, we have to combine the continuity relationship with other question types like continuity plus Bernoulli's equation. You can get pretty interesting with those. And then chapter 6 is just all about momentum. So another very narrow focus, single equation really that you're applying in chapter 6. So the format of exam 2 is going to be largely similar to the first exam, where there's going to be, my intention is to have 4 problem-solving type questions, and then I may have a handful of concept questions as well that are relatively low point value, relatively limited time that you'd need to solve it. So it's just going to be a short answer where I'm trying to assess your understanding of some concepts. Yes?
On the homework handout on the MU Online, you can no longer access them on there.
That's true, but the handouts are someplace else. So let me show you where those are available.
I'm just talking about you compare what your original question was asking.
Yeah, I understand that. So if you go to Blackboard and go to the course page, here under homework assignments, the handouts are available here. So they vanish when the assignment is submitted, but they're all still available above that.
Okay.
Are there other questions? All right. So today we're going to talk about some additional fluid momentum applications. If you want to get an early look at this assignment, I'd encourage that. We'll still have some time on Thursday to talk about it in class. We'll do some more examples on Thursday that may play into that assignment. But the examples we're going to work today are related to fluid jets and vanes. Before we get into solving those, though, let's consider this one that you had on the homework that just was submitted. So this was a combination type problem where it's more than just the momentum. The momentum aspect of it is relatively simple, but the combination part is then where you're asked to find H. So what I want to focus on just now is how did you know what to select as the control surface? Do you feel like you have a clear idea of what's the rule for drawing the control surface inside of which is the control volume? What's kind of the rule of thumb that you used on this one? How do you know where to draw that dashed line that represents, remember, we're keeping track of flow in and flow out. The equation that applies here is the sum of the forces in the y direction is the mass flow rate out, velocity out in the y direction, minus the mass flow rate in times the velocity in the y direction. So this is the governing equation for the momentum aspect of the problem. And so we're keeping track of flow out and flow in. So how do you know what to draw as the boundary for where the flow in and the flow out occurs?
We draw from where the intake is and then we're up to where the outtake is.
Well, but that's subjective. I mean, you're right. You'd want to enclose the intake and the outtake, but, you know, for example, you could say here's the jet coming out, you could say here's the flow out, and then this wedge is changing the direction. So you could say here's where it's coming in, and in theory someone could draw the control surface in the wrong place, and so I'm implying that this is the wrong place to draw the control surface, and the guidance I give you is that this would be the wrong place to do it for momentum because nothing's changing. The momentum in and out of the control surfaces as I've drawn them here on the whiteboard would be a pretty uninteresting problem to solve because nothing's changed necessarily. There's no change in direction, whereas if we go a little bit higher, this wedge is changing the direction. So what you should pick as your control surfaces is some boundary that encompasses where a change occurs. And so this wedge is forcing the flow to divert. It was exclusively vertical, and now there's this fan-shaped jet that's going partly vertical and partly in the horizontal plane. And so when you're finding the velocity out, then you just find the velocity out that's in the vertical component, the vertical component of this out velocity. So the principle that we can take away from this that we're going to apply for the rest of the examples today is when you're drawing your control surface, if there is a tank, you should enclose the tank. Otherwise, if it's a matter of deflection, you should draw it so that the deflection occurs inside of the control surfaces. All right, so with that in mind, we're going to work through today a fluid jet type problem, and this is the classic fluid jet type problem. We're going to work through a vane problem today, actually 2 fluid jet problems and 1 vane problem, and then in class on Thursday, we'll move on to the more complicated question of nozzles. And this is more complicated for a couple of reasons that we won't get into now. But remember that for this governing equation that can be applied in the x direction or in the y direction, the left-hand side of this in words, the way that we would interpret what this sum of x and the sum of the forces in the x direction, what that means is the force required to hold the system steady. And it's important that we are very specific about that because sometimes a problem may ask you what force did the jet apply to the deflection surface. And that would be the equal and opposite to what this equation actually gives you. This equation is asking what external force do you have to apply to hold the system steady, and the system otherwise wouldn't be steady because of what the jet is doing to it. So just keep in mind that what we're actually calculating is an external force that has to be applied. All right, so we'll get some applications both ways of that, just so that you get some experience interpreting the problem statement. Okay, this first one is a tank of water where a fluid jet is coming in. And we're wanting to find out the reaction in 2 directions. The horizontal reaction to this fluid jet coming into a tank full of water, and the vertical reaction. And if we're considering the tank, then the stop block that's outside of the tank, we can think of it as just maybe like a brick that's on this horizontal surface. It's pressing to the right because our instinct kind of tells us if the jet is going in, then this tank would have a tendency to slide to the left. Assuming that there isn't enough friction interacting between the tank and the surface. I mean, it could be that there's enough frictional resistance that it wouldn't move anyway. But let's just assume that it's a frictionless surface. And, it's ice, greased ice. And there's a tank of water, and the jet, if it was just impacting this tank of water, it would be pushing the tank to the left. And so the stop block is going to be pushing to the right. And in this first bullet point, what it's asking is what force does the stop block apply to the tank so that the tank doesn't move. And then the second part, where we're working in the y direction, we're going to want to find out the force that's acting on the bottom of the tank by the greased ice or whatever it is that the tank is resting on. Okay, so the characteristics of the jet that we have defined is the velocity of the jet, its fluid properties, since it's water, that tells us the density of the liquid. And then by knowing its diameter, we can assume that it's circular in shape. The cross-sectional area is circular. So that jet's going in, filling the tank, and we also know the mass of the tank and how much water is in there. And that'll come into play when we're calculating these vertical forces. All right, so I've got the forces in the Y written on the board. The forces in the X are just some of the forces in the X is the mass flow rate out, velocity out, specifically in X, mass flow rate in, velocity in X. So I'll remind you that m dot, mass flow rate, number one, in the equation here, it's not asking for the component in a direction because the mass flow rate is a scalar, which means it'll never be negative, and we don't have to keep track of what part of the mass flow rate is vertical versus horizontal because all of the directionality of the momentum is accounted for in the velocity. So what we do need to remind ourselves is that when we're doing calculations like this, that to the left, when we're working in horizontal, to the left is negative, and that negative sign needs to go into the velocity term, and to the right is positive. Okay, so enough setup. I'm going to pause for a moment, give you some time to calculate the force that the stop block applies to the tank. And remember, this equation, the interpretation is the force required to hold the system steady. Okay, so are we going to have to flip the sign once we've calculated? And the answer is no. That's what the stop block is doing. The stop block is holding the system steady, so whatever we get from this equation is going to be the answer to this first bullet point. We're not going to have to find the equal and opposite reaction. Okay, in my case, before I even started doing the momentum calculations, I just calculated some of the preliminary stuff I knew that I'd need, like the area of the jet, the weight of the tank, the weight of the water. So we'll need that later on, so calculated it from the beginning. Now, in the X direction, we can tell just by inspection that this jet that's coming in, most of its effect is going to be vertical. Less of its effect is going to be in the horizontal direction because, I mean, 70 degrees, that jet's not totally vertical, but it's mostly vertical at 70 degrees. If it was 45, then the effect of its momentum would be split half and half between the vertical reaction and the horizontal reaction. So just before you start putting the numbers into the calculator, have a relative sense for where the momentum is going, like its breakdown between horizontal versus vertical. And so most of it's going to be in the vertical reaction rather than the horizontal reaction. So keeping that in mind, you calculate the mass flow rate, 10.6 kilograms per second, and I saw that a lot as I was walking around. And then here for the force in the X direction, there's nothing going out. It's just a tank that's receiving all of the inflow. So we have to retain that negative sign there. And then since it's to the left, the velocity also has a negative. So those two negatives are going to cancel each other out. And then the 0.342, that's the effect of the cosine of 70. So it tells me that less than half of the reaction is going to be in the horizontal direction, and that's what I'd expect to see. Okay, so on momentum problems, it's really important that you bend over backwards to specify the direction and also what you've calculated. So here in words, I'm saying that this is the force required to hold the system steady. And so there's no confusion about whether I thought that was the force of the jet on the tank. I'm saying, no, that's the external force applied to hold the tank system steady. And then the direction is to the right. And so it was positive, which implies it's to the right, but then I've eliminated any uncertainty by also below that saying its direction in words. Any questions about that first part in the horizontal direction? Okay, now in the vertical, we again have no flow out, just flow in. This time taking the sine of 70 or the cosine of 20 for our direction factor. Mass, flow rate, velocity. So the negative sign again for velocity, because if we look at the direction of that jet, it's down. So we have to retain the directionality in the velocity calculations. So this F sub y is the upward force required to resist the jet. And then the total force, the way that the question asked it, is the force acting on the bottom of the tank. And so the ground is pushing up against the tank, equal and opposite to the momentum effect, and then the weight of the tank and the weight of the water. So there's three things together that are going to go into our final answer. The momentum plus, okay, so here's the momentum, 149. The weight of the tank was 5 kilograms, and so we found that that's 49.05 newtons. The weight of the water, 196.2 newtons. So altogether, I overshot. 394.6 newtons, and the direction is up. Any questions about that example? Okay. Well, let's look at a small curveball then in terms of what the question is asking versus what the formula will give you. Okay, so in this next example, this one's not in the notes, so you'll just have to copy it down on a separate piece of paper. We're trying to calculate what force does the jet apply to the plate. So remember, the equation says what is the force required to hold the system steady. So if we were going to just plug into the equation, what we're going to calculate, we can tell that the jet's pushing to the right, so you're going to have to push to the left in order to resist that effect of the jet. So we'd be pushing on the plate to the left, but the question is asking what external force does the jet apply to the plate? So now the perspective is this plate, what reaction is the jet causing? So the jet's going to be pushing the plate to the right. So keep that in mind when you calculate the sum of the forces in the x direction. What you're actually going to report is the equal and opposite of that. What we know is the velocity as the jet before it interacts. This is kind of like a metal plate with a ring in the middle. It looks like a maybe similar to that Orifice plate that we used in the lab, where it has a small diameter hole, and this one's even contracting a little bit more, so that's pretty cool. We can calculate the coefficient of contraction on this one. We've got two different diameters. We've got the large diameter and the small diameter, and we want to find out what force is the jet imparting on the plate. A couple of notes about this example. So you'll notice that V and V, so it's the same in and out. The magnitude of the velocity hasn't changed. That portion of the stream that passes through the opening in this orifice plate, the magnitude of velocity in is 90 meters per second and out is still 90 meters per second. Sometimes I'll give you problems where the velocities stay the same. Sometimes the problems, it mentions the velocity slows down. In this case, it's the same. The other thing is that, this vertical component, we assume that it cancels out in the y direction. So we're only having to find the forces in the x direction as a result of this change. Okay, so this one you'll have a different mass flow rate in versus out because the diameters are different. So we need to find the mass flow rate in. It's a big one compared to the mass flow rate out is relatively small. Needed the area for both of those in order to calculate the mass flow rate. So then you can see the substitution is we have the mass flow rate out, the velocity out's the same, 90 meters per second. That's positive because the jet's moving to the right. And then minus in, because the jet's just moving to the right, so it's positive. And so the negative sign here is going to subtract the amount of momentum that's imparted. So we have negative 55,824 newtons. That means that the force required to hold the system steady is to the left. You know, like if we were trying to apply an external force to this plate because we knew the jet's interacting with it, we would have to push on the plate to the left. But the question is actually asking what force does the jet apply to the plate, not the external force we would hold it steady with. So then it's equal and opposite. So 55.8 kilonewtons to the right. Any questions about that one? Okay. All right, this is the last one we're going to look at today, and I like this one because we're going to have to apply the continuity relationship in order to solve some of the information that then we'll substitute into the momentum equation. So let's see, the given information we have is we know the velocities for each of these jets. The jet coming in is going to be deflected partly out up to the right, part of it's down and to the left. So take note of those directions. You know, when you're solving in the x direction, stream 2 will be positive, stream 3 will be negative since it's to the left. And then when we're working vertical, stream 2 would be positive because it's up, stream 3 will be negative because it's down. But what's not given is the mass flow rate at location 2 and at location 3. We only know the mass flow rate coming in. That's stream number 1. But what we are given is the diameter of the jet that's coming out here at 3. And it turns out that with the velocities, then that's going to be enough information for us to find the mass flow rate at 2 and the mass flow rate at 3. So I won't spoil the fun too much, but you're going to have to start with the continuity equation to find out what is m dot 2 and what is m dot 3. Actually, you'll do that in reverse order. You'll solve for m dot 3 first, and then you'll be able to find m dot 2. Once you know the mass flow rates, then we can substitute it into the momentum equation. Then we have to look carefully at interpreting the word problem here. It's saying, what forces does the water jet apply to the deflection plate? So, similar to that last problem, you're going to find the equal and opposite reaction to what you actually get out of the momentum equation, because this question isn't asking the force required to hold the system steady. It's not asking what force is this reinforcing beam applying to the plate, but it's asking what's the water jet doing to the deflection plate. Okay, so starting with continuity equation to find m dot 3 and m dot 2. I've got the mass flow rates up on the screen now if you want to double check your value for M.3 and M.2 and how that was calculated.